So next we'll have introduction to Qiskit, a very interesting class. This is what where you'll get your hands dirty on coding and real working with quantum computer. That's why you are here, right? So all these things are done. All this theory, quantum mechanics parts are done. Now I have with me my junior researchers at Qkrishi, Rupa, and Sairupa is here, and Rohit. Yeah, both of them are here. I think you have met Rohit yesterday, and Sai is also Sairupa is also a junior researcher. Both of them have worked with me with the quantum games, and we recently got into the IEEE posters. So there are two brilliant people in Qiskit, so they'll be taking you through the first steps on Qiskit. Handing over to you, Rupa and Rohit.
Hello everyone. So good afternoon. So let me present my screen. Can you able to see the slides? Hello.
Yeah.
Yes, Rupa.
Yeah, cool. So Qiskit today. What is Qiskit? So Qiskit is a software development kit developed by the IBM researcher. So where we can work with the different circuits, gates, and application modules, and some packages, very vast packages, where we can deploy the hands-on quantum algorithms using this. Quantum computers, like when we used to write the algorithms, we have to use many gates and optimization techniques, measurements, etc. Right? So Qiskit able to provide the module for overall execution. And let's go with an example. So what we can do. I just like to take the practical scenario. First, I'm a user who just want to execute a quantum algorithm. So I have written my code in the Python language. The Python language contains the quantum circuit with some gates, right? After this Python code, with the help of this gates, where this Python code represents, this quantum circuit then undergoes the transpiler. Transpiler in the sense translator plus compiler, where this circuit which I have created is converted into the same equivalent source code. But there you can see in the picture, like input I have given is this, but the output generated after the transpilation is this, right? So output circuit will be like this so why it has converted like this? In between there are many steps. I don't want to go deeper because it's based on the topology of the hardware and hardware components which are available in the libraries. So after this, the output circuit is converted into this. Then it's a transpilation. After that, from the browser, by HTTP request, then it gets connected to the IBM server. After the combination of IBM server components plus some hardware calibration techniques, then this circuit, this output of the transpiler will be converted into a pulses or electronic pulses. There we can use electronic pulses. These electronic pulses goes to the compiler. After that, using some device drivers and some firmware components, it goes to the chip where we used to manipulate the signals, and with some techniques, something like optimization techniques and optimization mechanics, something like that. After this chip, it gives the output. the output is carried out through the device drivers. Then after we measure, uh, after applying the measurement to the electronic signals, then we will able to get this classical output in the sense we will able to get the binary format like 00 and 01, something like that, after measuring the signals. Then this output will be able to display to the user like what's the analysis, like how much percentage probability of getting 00 and 01. So that's the entire process when we run the code, right? After that, let me explain. So, what's Qiskit? So, with the help of Qiskit, if you are the novices who wait, you don't know how to start and wait to uh, get the references or books, something like that, you can learn uh, where there are many textbooks, tutorials, and videos available in the Qiskit, and there are many community events in the sense like there are many programs like Global Summer School, and there are many challenges which is carried out by IBM throughout the year. So where you can participate and have fun over there, and let's contact with the people and learn more through these challenges. After that, if you are planning to pursue your career in IBM, mainly in quantum computing side, it's better if you have an advocate certificate. There might be a chance of getting into the IBM. After what the Qiskit has, there are many applications in the Qiskit, where the people can explore the machine learning techniques using quantum computing modules or packages. Then Qiskit Nature, which helps to create a algorithm for chemistries like finding the ground state and finding the excited states and spin orbitals of a molecule or something like that. The nature is related to the chemistry. After finance, different financial optimization techniques, etc. And then support, you can get support from GitHub, Stack Exchange, and some documentation where you can run the cells by your own using the code snippets or something. Then installation, that two ways to install this Qiskit. First, you can run through the cloud, where you just register in the IBM Quantum, uh, register and sign into it, and then you can able to see all those quantum computing lab and quantum composer and different things where you can run it on online. So if you want to install it locally, then install the Anaconda, where Anaconda is the set of Python libraries, right? So there you can install it if you're it's compatible to the Windows, Microsoft, Linux based on your OS. Then after that, install next. After that, you can go to the Jupyter notebook right here. Then then at the start in the start menu, you just search the Jupyter notebook. There where you can see the notebook in the menu bar. Click on that, and you can able to see all the files that are present in your C drive or D drive, or in the file manager. You can able to see them in a browser, default browser. After that, create a folder of your own and run the cells. So how you run, you have to install this code like pip install Qiskit. uh, then after, you have to import the libraries from the Qiskit and run the circuits. So that's the overall view of installation and how Qiskit executes when the user have given the input. Then over to Rohit will explain you the code, and he will walk through some circuits. Over to Rohit. So, and before that, if till now, if you have any doubts, please let me know.
Yeah. Thank you, Rupa. I guess I'm audible. Um, Yeah, is there any disturbance in my voice? No, right?
No, 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 no.
Fine,
I'll
fine, fine.
start sharing
So,
the screen.
yeah. So hi guys, I'm Rohit. I'm really excited to take this session, and I hope Ruba made you all acquainted to what Qiskit is and how do you install it and how you can access Qiskit online using the IBM Quantum. So just wanted to know something. Do you guys already have a IBM Quantum account or no? Can you please answer me?
Oh, sir.
Yeah, I have.
Yes, I do have one.
Fine, fine, fine. So you have started using it.
Like tried some basic, really basic things,
All
like
right, all right.
putting some hard gates and all.
Okay, fine, fine, fine. So those who have a Quantum account, I'll be sharing my screen shortly, and if you want, you can start coding with me. And others, no need to worry. I'll be sharing the Jupyter Notebook files with you guys later, so you can use that. So people who already have an account, it will be good if you open it and then just start coding with me. So fine. So let's get started. Uh, I hope I'm sharing my screen. Are you guys able to see my screen?
Yes.
All right. So if you have any doubts in between, please speak up because since I'm sharing my screen, I may not be able to noise some of you raised your hands. Okay. Fine, fine, fine. So yeah. So as Ruba mentioned, Qiskit is a open source software development kit that you can use to uh, run quantum programs, build quantum circuits, and then use real quantum devices to run your programs. And frankly speaking, I was really excited when I got to know about Qiskit at the very beginning because, quantum computers are the epitome of technological marvel and you get to use it to run your program. It's really exciting. And I hope to share the same excitement with you guys today. So let's start using Qiskit and so all of you open your IBM Quantum account, log into it, and then open up IBM Quantum Lab, open a Jupyter notebook, and start coding. So that's what I did over here. Okay, all right. I'm using IBM
Rohit,
Quantum Lab
can
over
you
here.
just redo that for people? Like, just
Sure,
redo
but
over the screen.
I
Will
hope it
take
will
time.
take some time to load. Anyway, I'll try. Okay, 1 second.
Yeah, just the basic steps, people to start with.
Yeah, yeah. You guys can see my screen, right? Just type Qiskit in it. I've already done that. So open Qiskit. Yeah, it takes a few seconds to load the page. That's the thing. That's why I already had it open. No issues anyway. Yeah. So once it's here, just go to IBM Quantum Lab, and that's it. Your Quantum Lab is open for you. Before that, you have to, first make a IBM account and all those things which Rupa already mentioned in her presentation. Yeah. Then you have your files on the left side, and in that this is the file that I'm going to share with you guys today. So yeah, it works smoothly. So yeah, you guys can see the screen, right? Guys, yeah. So I hope my screen is visible and let's get started. Let's build our very first quantum circuit. So you guys know what a quantum circuit is? So quantum circuit is exactly like a electronic circuit. Well, not exactly in the sense there are similarities, but like an electronic circuit where you have bits and gates and all, a quantum circuit is just a sequence of qubits, gates, and measurements. You guys already know what a qubit is, right? A two-state quantum system. So any quantum program can be represented by a quantum circuit. So when you say that you run a quantum program, what you really mean is you executed a quantum circuit. So a quantum program means a quantum circuit. So what do you need in order to build a quantum circuit? You need qubits for sure, because those are the basic things that you require. Qubits, gates, and measurement. These are the three fundamental things that you require when you build a quantum circuit. So let's build a quantum circuit over here. And just like in Python, before you start writing a program, or the first thing that you have to do is you have to, import all the tools that you required from the corresponding libraries. And that's what I did over here. So from the Qiskit library, import these tools: quantum register, a classical register, and a quantum circuit. So this is what you need initially in order to, start building a quantum circuit. So what is a quantum register? So you guys know what a register is like in electronics. So it's like a ordered sequence of bits. It's like a box containing bits. So exactly same thing over here. Quantum register, instead of the bits, we have qubits. So quantum register is a ordered arrangement of qubits. And exactly like that, classical register is nothing but the register we have in our electronics, like ordered arrangement of bits. And then we have a tool that is called the quantum circuit. So import all the three things and let's start building. So first, let's assign a quantum register and name the quantum register. I've named it QR, and I'm telling Qiskit that QR is a quantum register that contains 1 qubit. So that is the argument of the function quantum register. It tells Qiskit how many qubits are there in the quantum register. So in the circuit that I'm building over here, I've used just 1 qubit. I need only 1 qubit. So I tell Qiskit that QR is a quantum register containing 1 qubit. And then I have to assign a classical register also. So what do? I tell Qiskit that CR is a classical register that contains 1 bit. Fine. I hope you guys are fine until here, up to this point. So yeah, then we tell Qiskit that we want to make a quantum circuit named QC, and the quantum circuit should have the quantum register QR and the classical register CR. So how many qubits does our quantum circuit QC has? It has only 1 qubit, and the qubit is contained in the quantum register named QR. Fine. Any doubts, guys? No, right? Fine, I'm moving forward. So we'll ask Qiskit to draw the circuit for us. That is qc.draw. And this is the circuit. I've already run the code, okay? Because sometimes it take a few seconds to run it. So that's why, in order not to waste time, I've already run it. And this is our very first quantum circuit. See, a qubit named Q0 and a classical register named qubit inside the quantum register and a bit inside the classical register. So this line represents a qubit, and the two parallel lines with a slash, it represents a classical bit. Okay, this is what our first quantum circuit is. And I know this is not that exacting because it looks pretty empty. So let's start adding gates to our quantum circuit. And I don't know if you guys know what a quantum gate is. So just think of it as a AND gate, NOT gate, NAND gate until now. So for the sake of the moment, just think of it as a electronic gate. So what does it do? A quantum gate, what it does is it does some functions onto the qubit and then gives us an output. So don't take my words literally for the moment, because electronic gate is way different from what a quantum gate is. But for the sake of the moment, let's assume that it's just like adding an electronic gate to your circuit. So that is what we do over here. We tell Qiskit that we need to apply a X gate onto the qubit in the quantum circuit. So we write qc.x of 0. So it tells Qiskit that we need to add a X gate to the first qubit of quantum circuit named QC. So I've written over here x of 0. You guys know why? Because in Python and in Qiskit, the elements in an array are ordered from the number 0. So it's like the first qubit is actually the 0th qubit. We don't call it the first qubit, we call it the 0th qubit, because in an array, the positioning starts from the number 0 onwards. So from this moment onwards, I'll be calling it the 0th qubit instead of the first qubit. You guys are fine with that, no? Guys, someone can speak up.
Yes, sir.
Any doubts? Fine with that, no? All right. So I'm applying a X gate onto the very first qubit of the quantum circuit QC. And then I ask Qiskit to draw it. So this is what we get. You guys saw, no? This quantum circuit with a X gate applied onto the qubit and a classical bit. So this is how we apply a gate to a qubit in a quantum circuit. Guys, just tell Qiskit what gate you are applying and to what qubit you want the gate to be applied onto. And so that's it. We have built a quantum circuit. So let's leave it here for the moment. Forget about the quantum circuit, and let's see how qubits can be visualized. So there is a tool in quantum computing that we use to visualize qubit. It's called a block sphere. So just think of it as a globe, and you can actually visualize what the state of the qubit is in on that globe. So it's called a block sphere. Fine. So let's build a quantum circuit and let's visualize the qubit using the block sphere. So first we need to import block sphere from the Qiskit visualization library. So this statement actually does that. It imports the block multivector, which is nothing but the block sphere, from the Qiskit visualization library. Fine. So let's build a quantum circuit. Again, we are using the same name for the classical quantum register over here. So we say to Qiskit that we need a quantum register named QR containing 1 qubit. We need a classical register called CR containing 1 classical bit. And we have to make a quantum circuit containing quantum register QR and classical register CR. And we name the circuit as QC. Now using the block multivector command, I visualize the qubit. So I ask Qiskit to visualize the state of the qubit on the block sphere. So this is what we get. This is a globe onto which along the z-axis you can see an arrow. So this means that the state of the qubit is actually the zeroth state. So I already told you, I think you guys know what a qubit is, right? Guys, you already know what a qubit is, no?
Yes, sir.
Okay, so a qubit has 2 states, 0 and 1. So we use the block sphere to visualize the state of the qubit. And you can see that the arrow is pointed along the z-axis, and that corresponds to the state 0. Now let's see what happens when we apply a X gate. So yeah.
So why is the state of the qubit is 0? Like we haven't defined the state, right?
Yeah, so sorry, I had to tell you that before. Forgive me. So in Qiskit, whenever you make a qubit, when you do not apply a gate or anything into it, the default state of the qubit is 0. Got it? So all qubits
Yes,
are
sir.
initialized to the state 0 by default. Fine.
Okay, sir.
So that's what I've written over here. Qubits are by default in the state 0. Okay. So now let's apply a X gate onto the qubit and let's see what happens to the state of the qubit. Fine. So consider the X gate is nothing but a NOT gate. You guys know what a NOT gate does in classical computers, right? What does it do? Someone can answer me, please.
Just inverse the.
Yeah,
It is 0,
exactly.
it will be 1.
Yeah, so if you have a 0, it will give you a 1 as an output. And if you have 1, it will give you a 0 as an output. So yeah, that is what the X gate in quantum computing also do. If you have a state 0, it will convert it into state 1. And if you have a state 1, it will convert it into state 0. Now let's apply a X gate onto the qubit QC dot X of 0. And then let's plot it and see what happens. The state got inverted to 1. Got it? So it's like initially it was like this. The state was aligned along the z-axis, positive z-axis. That means the state 0. And what does the X gate do? It does a rotation along the x-axis with the x-axis at center. It does a rotation by 180 degrees. And what happens? The state of the qubit is changed to the state 1. You guys got it? Or any doubts? No doubts, right? Okay, so someone can tell me what happens if I add another X gate to the same qubit? Someone can tell me.
Sir, the state will again become 0.
Yeah. How?
So it just inverts the output, right?
Yeah. So I already told you what does an X gate does. The X gate does a rotation by 180 degree. So if I add another X gate onto the same qubit, let's do that over here. Let's apply another X gate onto the qubit. And what does it do? It again goes back to the state 0. Why? Because initially it was in state 0. Then when you applied a X gate, what happened? A rotation by 180 degree to the state 1. And again, when you apply it, what happens? It acts on the 1 state. Now it is in the first state. It again does a rotation by 180 degree, coming back to the state 0. So that is why we call that the X gate is its own inverse. So yesterday, I think you guys in the mathematics session, you guys were taught what unitary matrix and all are, right? So X gate is nothing but a unitary matrix containing 4 elements. So it's a 2 cross 2 matrix and it's a unitary matrix. That's why when the X gate acts on itself, what happens? It's similar to using a identity matrix. So when you apply X gate 2 times, it means that you are applying the identity. So it doesn't. It when you apply it 2 times, it does nothing to the qubit. But when it apply it once, it does a rotation by 180 degree. Fine. All right. So the only thing that is left for us to do in the quantum circuit is to add a measurement. Why do you need measurement? Someone can tell me, please. Why do you need measurements in quantum mechanics? Or what do measurements do in quantum mechanics? Anyone? No. Okay. So
Collapsing the wave function to get an absolute value.
yeah. So already in the morning session, you guys were taught quantum mechanics, the basis to it. So quantum mechanics is probabilistic in nature, or in other words, you can call it undeterministic, because you cannot say what the outcome of of a measurement will be. The only thing that you can say is that you have certain probabilities of getting a certain output. That's the only thing that you can say. So in order to know what state the system is in, you will have to measure it, and that's why we add a measurement to the circuit over here. But here in this particular case, you already know what the output is. What will be the output when I do the measurement? Let's see. I already the first the qubit was in the state 0. I added a X gate. What is the state now? 1. And when I do the measurement, what will be my output? Someone please comment. I have initially I had a 0th state. I added a X gate. So I got X gate converted the 0 to 1, and now I do a measurement. What happens? What
It
is the
will be
state?
1.
Yeah, so it's like take it as a coin. So the coin is lying on table heads up, and I inverted it. Application of the X gate, I inverted it, and then now it's tails, right? So when I do the measurement, I know it's tails. So with 100% probability, you can say that the output will be 1 over here. So how do you apply the measurement? So this is the program that we have over here. We have a quantum circuit with a quantum register containing 1 qubit, a classical register containing 1 bit, and then we apply a X gate onto the qubit, and then we tell Qiskit that we want to measure the state of the first qubit in quantum register. Here we only have 1 qubit in the quantum register, but we have to specify the order of the qubit. So we are saying that we are measuring the 0th qubit of the quantum register QR, and we are encoding the result of the measurement in the classical bit. So that is why we need classical bits in our quantum circuits. Classical bits are used to encode the result of the measurements. Fine. So that is what we do over here. We measure we measure the first qubit, and we encode the result of the measurement in the classical bit. Fine.
If
Okay.
we use more than 1 qubit, then we need more than 1 classical register, right?
Yeah, exactly. So that's why I already told you that you can control the number of classical bits that you need. Like for example, if you need 2 classical bits, let's change it to 2. Change this to 2.
But
And
one question, like
yeah,
we are using quantum computer, because if in the classical computer, if we need n bits, then but in quantum computer we can handle 2 to the power n bits.
yeah.
But here again we need classical register to measure the qubit. So
No. Classical registers are used to encode, to tell you what the output or the final measurement is. It doesn't give you 2 raised to n values. So suppose you have 2 raised to n values, you have a superposition of states, and when you measure it, you get only one state, and that state is the result of the measurement, and that result is encoded in the classical bit. Got my point?
okay, got it.
So it's not like you're using the classical bit to create the superposition, or classical bit to you have qubits in your quantum computer, and those are your memory devices. So instead of transistors in our classical computers, we use qubits. Got it?
Yeah, got.
Okay, fine. So as I already told you, if you want more number of classical registers, just specify it in the argument. Fine. So yeah. So we
Sir,
have built, yeah.
I don't understand the role of classical register here. In the
Yeah.
quantum, it was 0 to start with, then by applying the X gate, it turned to 1, and we
Yeah.
measured it 1. Now, what does the classical register do?
So that measurement process, right? You need to store that result of the measurement somewhere. Got my point?
Okay, so classical register is storing that
Measurement
final
final
measurement.
result. Yeah.
Okay.
Got it. That's why always in a quantum circuit, the measurements will be at the very end, or the at the very end, where the places where you want to measure it. You can't, simply add measurements here and there, because that will disrupt the entire thing. Got my point? So classical registers are used here to store the result of the outcome. It has nothing to do with the computation. The computation, everything, the gates, everything, all these are done on the qubits only. The qubits does the computation. You apply the gates onto the qubit. The classical bits we have over here just to store the final result of the measurement. All right. Any more doubts?
So it's just like the memory, like storing the final memory,
Yeah,
because we don't
fine.
want
Yeah.
the result to be probabilistic. We want it to be like to be
When
a
you
certain
do,
value.
the results will always be probabilistic.
Yes, sir.
In this, you have to, reframe your question in the sense that, in a quantum mechanical measurement will always be probabilistic. So it's like you have a wave function with, it's a superposition of the, probabilistic outcomes. And when you measure it, only one of it will be a outcome. It's like you have a coin, you have a probability of head and a tail. But when you do the measurement now, only you get either a head or a tail. And you store that information on the classical bit. Got my point?
Yes, sir.
All right. So, yeah. So now we have made the quantum circuit and we need a place to run it. We need a device to, yeah,
Rohit, one question.
yeah.
Above of the parallel lines is number 2.
Yeah.
But in the prefix is C1. What is the explanation?
Okay. So, that is because I have run the circuit 2 times. So it just says that I have run it 2 times. So it's just a feature of Qiskit, nothing related to the computation. It's because I have run it 1 time over here. I have run the same circuit over here, and then I'm running it again over here. That's why it says Q1 and C1. It has nothing to do with the computation. Fine.
Okay.
Okay. So yeah.
I also hope everyone is actually doing it yourself. In a computer that will be better for you, or else listening won't help you.
Yeah, guys. So yeah, all of you who has a quantum account, please do it along with me. You want me to slow down or what? Or is the face fine, guys? So I'm taking it as
Maybe
a,
pause for a few
Sir,
seconds. Think
yeah.
on.
we cannot keep up with the speed if we have to do the computer, if we have to write the code ourselves.
Yeah, sure. Take the time you want. So I thought that to complete it in 30 minutes. So that's why I went a little bit ahead. So yeah, whether you want me to stop and or pause, just let me know. Okay, no issues.
Or you can share that Jupyter notebook. We can
Yeah,
try it out.
I'll definitely share the Jupyter notebook, but it would be better if people can code along.
I mean, we are trying for the first time. We can't keep up with you.
Yeah, it's fine. It's fine. I'll share
Maybe you
share
can share the code now.
I'll share. Sorry.
You can share the code now, Jupyter Notebook now, and ask now. Help them with that.
Yeah. So yeah, I'll share it. Where do you want me to share it? In the chat.
WhatsApp. You won't be able to WhatsApp group में share.
Yeah. So I think I'll be able to share it in the WhatsApp. Uh, Yeah, so I've shared a PDF of the Jupyter notebook and WhatsApp. So if you want, you can refer to that. But because we have a time constraint, I think it is better if I move forward.
Yeah, please, please.
Guys, it's pretty simple. It's exactly like using Python. Okay, don't have to be intimidated about this. It's pretty simple. So just look at what I'm doing, nothing else. Okay. Yeah. So guys, focus on the screen. Yeah. So we have made a quantum circuit, and we need a place to run it. So in Qiskit, there are two types of devices on which you can run the quantum circuit. So the first device is called a simulator, and the other is called a real quantum device. So real quantum device are the things that you see when you type Qiskit in Google. The a pillar-like object which is a cryogenic tank and all. So that is what a real quantum device is. And you have simulators. So simulators are nothing but classical systems, which with the use of certain softwares, we are mimicking it to function as a quantum computer. Got it? So you guys may ask me, so if you can, mimic a classical computer to work like a quantum computer, why do you need quantum computers in the first place? So it's a valid question, but the thing is, you already know that if you have n qubits, there are 2 raised to n possible values, right? So in a quantum computer, because by very nature it is quantum mechanical, it can create the superposition and conserve it at the same time. But for a classical computer, you need to store all those 2 raised to n values at the same time. So you need 2 raised to n bits to store it, and that is like using additional memory, and so on. You lose the quantum advantage. So, but why do you need quantum simulators in the first place? That is because every quantum programs you can't send it to a quantum computer because there are very few quantum computers available. If you do send it, it will take a lot of time for them to run your programs and give you the output because there are too many programs to run, right? So you will be in a long queue. And for that, in order to avoid that, and for educational purposes, what we use is we use simulators. Got my point? Any doubts? Guys, no doubts, right? Okay. So
now we
yeah.
are using the simulator because number of qubits is less now. Like,
Yeah,
that's
because the number of qubit is less. So let's suppose so okay, so there are two types of simulators also. The first type of simulator, you can what it does is you can run it in your local device. So the laptop you are using now, some simulators work on your laptop. So what it does is by the use of software packages, it changes your laptop to work like a quantum computer by using additional memory. And you have simulators like that. Also, there are some simulators which you can access via the cloud on IBM Quantum. So that is because if in your local system, if the number of qubits are way high, let's say that for 50 qubits, you cannot run it in your laptop because your laptop does not have the memory required to code for 50 qubits. So if you have more than 50 qubits, what you do it, you use IBM's cloud simulators. Got it? Got my point?
yeah.
Yeah. Quantum computers, real quantum computers, the problem is that these are very expensive devices. You need to store it at very low temperatures, and it is prone to noise also. So that's why, in order for educational purposes and for most purposes in general, you can use a simulator. But if you need the real quantum advantage, which is the exponential rise in processing time, exponential, processing time and the storage, in order to have the quantum advantage, you need real quantum devices. But other than that, you can use simulators. Okay, fine. So I already told you that there are two types of systems on which you can run: real quantum systems and simulators. So where do you find all these systems? So you find all these systems in a place called provider. So consider the provider like a warehouse where you have simulators and real devices. So there are two types of providers. One is AER provider and the other is the IBM Q provider. So what is the IBM Q provider? The IBM Q provider gives you access to simulators and real devices which you can access via cloud. Got my point? So what you do is, if you want to run a code in a real quantum computer or a simulator which IBM has, what you do is you send the code to IBM and then they run it and give you the output. And the other provider is the AER provider. The AER provider has all the simulators which you can run in your local device. Got it? So first we will run the circuit in the AER provider, in some of the simulators in the AER provider. So let's first list down what all simulators we have in AER. So I have listed it down. So from Qiskit, import AER and check for the backends. So backends are the simulators or real quantum devices. We call them as backends. Got my point? Yeah. So these are the simulators that we have in AER, and we are focusing on two of these simulators, the quantum simulator and the state vector simulator. Where is that? Yeah, state vector simulator. We are focusing on both these simulators for the moment. And quantum simulator, I don't know how it is pronounced, but for the sake of the moment, let's call it quantum simulator. So what a quantum simulator does is it runs the code, runs the circuit multiple times in your local device. So when you want to run a code multiple times in your local device, what you use is you use a quantum simulator from the AER provider. So let's just first run this code, run the circuit in the quantum simulator. So this is how you do it. So in order to run it, first you have to import the AER provider from the Qiskit library. Then you have to import the execute function from the Qiskit library. So that is what is written over here. From Qiskit, import execute, and then let's name the quantum simulator as a simulator. So the simulator we are using over here is the quantum simulator, and we assign a job to the simulator. So what we do is execute the quantum circuit QC in the simulator quantum, and by default quantum simulator runs your quantum circuit 1024 times. So if I just remove this shorts, if I just remove it, what happens is that now when I run the code, it will automatically run 1024 times. So if you want to change it, like suppose you say that you want this 100 shows, just type 100. So by default, quantum simulator runs it 1024 times. And now when I run it, what happens? I get the output. And how many outputs are there? There are 1024 outputs. And I display it. And this is how I display it. Print counts. And what happens? You get the result 1. So the state is 1. We have already told you. I have already told you that the output of our quantum circuit is the first state. And that you get 1024 times. Everyone clear with this? Clear with this?
Now we have given shots is 100, so one should come 100 times. Right?
No, I didn't run it.
Oh, okay.
Yeah, I'm just showing you. Like if you want to change it, so yeah. Let's say 24. When you run it, it will show 1024 times. Got it?
Sorry. Like, could you repeat it again in a short way, because I was lost in the middle while I was trying to execute the code.
Yeah. What do you want me to repeat?
Regarding this execute and the simulator part is good about the code. Like,
you want me to explain the code?
Yeah.
Okay, fine. So the first line of the code is you have to import the execute function.
That so is. I just want to know what it's counting.
Count. Okay. I'll explain it to you. So when you execute the quantum circuit QC in the quantum simulator, the quantum simulator runs it and it gives a count of how many outputs you got, how many times. Got it? So if you have two outputs, let's say that when you run it, the quantum simulator got 0 10 times and 100 times. What does it do? It displays the count, how many times you got the state. So here, when quantum simulator ran the circuit, it got the state 1024 times. So this is a count. Got my point?
Okay.
You really understood it, no? Or you want me to explain it again?
No, I got it.
All right. Fine. So, yeah.
So it might seem a trivial question, but why were we using simulator to run a circuit? Like, what was the reason of? I didn't get the job of the simulator.
Maybe we can discuss it later. Let him complete. You can ask him after the class. He's also.
Yeah, I'll be available all the time. So if you want to ask me something, just you can do it later also. Okay. So simulator is nothing but you can have two types of devices, simulator and real device. Because a real device may not be available all the time, you can use a simulator to run your code. And the AER simulator has the AER provider has the simulators which run on your local device. So what you can do is if you have very few number of qubits, you can use your own laptop to function as a quantum computer. In order to do that, you need the AER provider. Fine.
Yes, sir.
All right. So let's plot the results. This is what happens when you plot the results. You can use a histogram, import the histogram from the Qiskit visualization library, which we used earlier to import the block vector, and plot it. So what does the plot says? With a probability of 1, you got the state 1. Got it? All right. So this is what the final code will look like. This is the entire thing. The everything that we did over here, from creating the circuit to running it, that is what given over here. This is the final code. I'll share this notebook with you later so you can go through it, just explaining it so that when you read the notebook, you'll understand it. Yeah. Now, instead of the quantum simulator, we will use the state vector simulator from the AER. What does the state vector simulator does is it runs the circuit just one time and gives the final state vector of the output. So this is instead of quantum simulator, just type state vector simulator and run it. This is what the result is. So if you can use LaTeX to display it in a neat manner, and yeah. So this is the state vector. This state vector corresponds to the. So read it as a column vector. Okay. Here it is displayed as a raw vector, but read it as a column vector. Column vector 0, 1 corresponds to state 1. Guys, understood? Because the final state of our circuit, final state which you get after running the circuit is 1. You can use a state vector simulator to run the circuit one time and get the state vector of the final output. Got it, no? Yeah. Yeah, anyone any doubts? No, okay. So now let's look at another gate. So here we are creating a superposition. You know what a superposition is, right? So if you have a coin, when you toss it, and when the coin is in midair, you have a probability half that it is in the it is heads, and you have a probability half that it is tails. That is exactly what a superposition over here is. So when you apply a Hadamard gate to a ket to a zero state, what happens? It creates a superposition of the 0 and the 1 state. Understood? This gate is called a Hadamard gate.
They'll study gates in the next session, so we can continue.
Yeah. So creating a superposition, instead of applying the X gate in the first circuit, here we have applied a Hadamard gate. Okay, the exact same code, but just that we have applied a Hadamard gate over here. And then what we do is we plot the state of the qubit. And when you plot it, what happens? It is halfway between a 0 and the first state. So it is not a 0 state, it is not a first state, it is halfway between a 0 and the first state. So that is what we call a superposition. And now we'll use the state vector simulator to see what state it is in, and we get the state vector 1 by 2, 1 by 2, column vector 1 by 2, 1 by 2, which is nothing but this. Got it? So that is the state of the qubit. And now we add a measurement. Exact same way as we did for the X gate, we add measurement. We say to Qiskit that we are measuring the first qubit and we are encoding the result in the classical bit CR, and this is what we get. And yeah, now when you do the measurement here, the output is probabilistic. Sometimes you will get 1 and sometimes you will get 0. That is what so when you do a measurement, what happens? The wave function collapsed, and each time you do a measurement, you will either get 1 or you will get 2. So we will use a quantum simulator. The quantum simulator runs the circuit 1024 times, and we are plotting the result. So this is the result. It got the state 1 518 times and the state 0 506 times. So it's almost the same as the probability. Like the underlying probability was half. So it's like a coin in midair. Half 1 by 2 to get probability of getting heads and 1 by 2 probability of getting tails. The exact same thing over here. 1 by 2, we had the underlying probability was 1 by 2 to get 0 and 1 by 2 to get 1. But when you run it, what happens? So it's like tossing a coin 100 times. You will get 60 heads, 40 tails, but still the underlying probability is half. 1 by 2, 1 by 2. Got it? Yeah. So that is what is over here. When you run it multiple times, each time you run it, you will get a different result. Fine. But the probability will almost be 1 by 2 and 1 by 2. Yeah. Now, this is the exciting part. We are using a real quantum system to run this circuit. So in order to do that, instead of AER, you will have to import the IBM Q provider. Okay. And then you will have to check which systems are available. So in order to do that, you can either ask your code to find out the least busy system, or you can check it on your own. In order to check it on your own, what you have to do is just click here, go to computer resources, open it, and look for yourself what all systems are available. So yeah, these are the systems that I have access to. I am a very amateur level programmer, so I have access to all these systems, and the top 6 systems, these are real quantum systems. The real deal. These are real quantum systems, and as you see, they have very few number of qubits, 7, 5 qubits, yeah. And then you have simulators. So if you want to run a circuit having thousands of qubits, you can actually use this simulator to run it. And there are various other simulators. So I need a quantum computer, real quantum computer to run it. So I can select from these 6. I can select one from the 6 of these real devices. But here what I did is I asked the code I am asking Qiskit to find a system that is least busy, a system that is having very few jobs to do. So many other people are also using the system. I also need to use a system. So my code will actually be queued, and I want a system that is least busy. So let's say that a system that only has 5 jobs remaining to do, I can use that because it is least busy and I'll get my output within a short time. So here I am asking the Qiskit to provide me a real quantum device. So that's why I said not a simulator. See, not x.configuration.simulator. I'm telling Qiskit that I do not want a simulator. I want an actual quantum device, actual quantum system. Yeah. And Qiskit told me that the least busy quantum devices, the quantum device named IBM Q Bellum. So the Bellum device is least busy. It can accept my job and run it. So this is so next what I did is I assigned the job monitor. The job monitor, what it does is it tells me what is the position of my code in the queue. So as I already told you, that various other people are using the device. So your code will be queued, and the job monitor tells you what's the position of your job in the queue. So yeah, so once you run it, it will take a few minutes to run your job because as I told you, it's in a queue. And after I run the job, exactly like you did for the other simulator, for the quantum simulator, you display the state, and this is what you get. Almost a similar output as we got over here. And I told you when you do it multiple times, the probabilities may change, but the underlying probability is still half and half. Yeah. So yeah, sorry I had to rush because of the time constraints, but yeah, this is my presentation about Qiskit, and there are various other gates that you learn later. You can use all these gates to make quantum circuits and run it in real quantum devices. Got it, guys? Any doubts? I'll share this, so don't worry about all these codes and all, okay? About the syntaxes and all. I'll be sharing my notebook, so you'll get to know it. You can learn it on your own, no issue with that. I just had to show you what Qiskit is and how do you use it. So don't worry if you forgot all the lines of code and all here, no issues. I'll share the notebooks. Fine.
That was
so
great
shall
presentation. Yeah, Rohit, thanks for that.
Yeah.
That was
Shall
great
I stop
presentation.
sharing?
Yeah, please.
A small
thanks.
question.
Yeah.
Maybe
sure.
we can.
Okay.
Yeah. So the thing is that we have the next session at 1:30, so we'll be able to get back by 1:30. That's it. So we'll also have a Qiskit session out at 3:30, so we can ask all the questions there. That's better. Or do you want to clear it now, so we can take it back after the class? So Rohit, that was a great session. Thanks Rupa and Rohit for wonderful session Qiskit. As Rohit said, all the codes are available online. You can search online and get familiar with it. So we also have other experts like Rohit, me, and Sairupa, and other experts that is coming to help you out. So don't worry about this. And the next session is at 1:30. So go back, get your lunch as quick as possible and come back at 1:25 something so that you can start at 1:30. So see you. Bye bye.
So the doubts can be asked at the 3:30 sessions, right?
Exactly. All these
Yes.
are regarding Qiskit, you can ask there, or else I'm there, Rohit is there. Come back as message in the group. Will be clear. No issues.
Okay, fine. Thank you.
Thank you guys. Bye.
Great session, Rohit. Bye bye.